Hello everyone, I am Casey. I will be the first reporter of Group 10. So without making this any longer, let us start with our introduction. Household appliances like washing machines and TV were usually highly inefficient when they were first invented. But over the years, they were optimized to reduce energy loss and perform better. Now, washing machines were optimized over a period of time to produce fewer vibrations and noise. Inside of the washing machine has a spring suspension to hold its body when it is working. With that, it can lessen the vibration and noise when the washing machine is working. And this kind of isolation is under the passive vibration isolation. Vibration isolation is the process of isolating an object, such as a piece of equipment, from the source of vibration. Vibration is undesirable in many domains, such as engineered systems and methods have been developed to prevent the transfer of vibration to such systems. Vibration propagates via mechanical waves, and certain mechanical linkages conduct vibrations more efficiently than others. High vibration levels can cause machinery failure, as well as noise levels. A common source of noise in the building is the vibration of machines that are mounted on the floors or walls. Obviously, the best place to mount a vibrating machine is on the ground floor. Unfortunately, this is not always possible. So with the help of passive vibration isolation, it makes use of materials and mechanical linkages that absorb and dump these mechanical waves. As well as the active vibration isolation involves sensors and actuators that produce disruptive interference that cancel out the incoming vibration. With the passive methods, isolation is achieved by limiting the ability of vibration to be coupled to the item to be isolated. This is done using a mechanical connection which redirects the energy of vibration before it gets to the item to be isolated. These are often used in machinery mounts or in a vehicle since they absorb shock and attenuate some vibration. Now, we are done with the introduction. The next reporter will explain the first and second problem about the vibration insulation problem. In this project, we use this model to illustrate an important fundamental principle in the design of a passive isolation system.
Hi everyone, I am Nina, and I will be the second reporter of Group 10. So, let's start! For question number 1, denote by y of t the displacement of the platform from its equilibrium position relative to a fixed frame of reference. Relative to the same fixed reference frame, let u of t represent the displacement of the plant floor from its equilibrium position. Shows that the differential equation for the motion of the platform is where W sub O is equal to the square root of K over M and zeta is equal to Y over 2 square root of MK is a dimensionless parameter known as the viscous damping ratio. For the solution, apply Newton's second law of motion, which is m multiplied by the second derivative of y plus gamma multiplied by the first derivative of y plus ky is equal to 0. Note that y minus u is the total displacement of the setup between the equipment and the floor since u is lessened in y. Thus, the equation will be divide all terms by m and then use the equivalent values or the values given in the problem, which is w sub o is equal to the square root of km and zeta is equal to y over 2 multiplied by km for us to be able to get k. After getting the value of k, we can now substitute it to this equation of zeta, which is zeta is equal to y over 2 square root of km. Substituting the value of k, and after a series of derivation, we were now able to obtain 2 multiplied by zeta multiplied by w sub o is equal to y over m. So after a series of computation and derivation, we were now able to arrive to the final answer. For question number 2, denote by g of iw the frequency response of equation 1, that is the ratio of the steady state response to the harmonic input u of t is equal to ae raised to iwt. The transmissibility of the platform mounting system is then defined to be the corresponding gain function. Tr is equal to the absolute value of g of iw. Show that Tr can be expressed as For the solution, let us consider a passive isolation system. Having a mass of m attached to a spring of stiffness k and a viscous damping with damping constant y, there is a mounting platform which is under a harmonic input, which is u of t is equal to ae raised to iwt. The spring force that acts on the system is equal to kx is equal to ky of t, which is motion is in vertical direction. The damping forces is ry of t, and the amplitude of vibration is capital A. So the maximum value of these forces will be like spring force is equal to Ka and the damping force is Rwa. So now we have a force diagram with equation of motion. Refer to equation number 1. So under harmonic vibration, we have u of t is equal to a multiplied by I multiplied by w multiplied by e raised to I wt. Then t is equal to negative a w squared cosine of wt plus I sine of wt. So the obtained value, substitute it to equation number 1. So after substituting the value to equation number 1, we are now able to have our free diagram. So before we are able to obtain the value of transmissibility, we must first identify the resultant force, which is we will calculate using the equation of Ka squared plus Rwa squared. Also, the disturbing force F when caused vibration is where zeta is the damping constant. Since we are able to calculate the resultant force, we can now move on to calculating the transmissibility. So, using the equation of transmissibility, which is Tr is equal to Ft over F, we can now substitute the value of the resultant force to the equation. After doing so, we are now able to obtain the required expression for TR.
Hi, I am Kim Andrew Soliman and I am the next presenter for Group 10. Plot the graphs of TR versus the dimensionless ratio omega over omega 0 for zeta equals to 0.1, 0.5, 1, and 2. For what values of omega over omega 0 is TR equals to 1? Explain why the graphs imply that it is desirable that the mountings have low natural frequency in order to isolate the vibration source from the equipment platform that is using low Sims x, y, zeta 1 is equals to 0.1 semicolon zeta 2 is equals to 0.5 semicolon zeta 3 is equals to 1 semicolon zeta 4 is equals to 2 semicolon y1 is equals to square root 1 plus 2 times zeta 1 times x raised to 2 over square root 1 minus x raised to 2 squared plus 2 times zeta 1 times x raised to 2 semicolon y2 is equals to square root of 1 plus 2 times zeta 2 times x raised to 2 over square root of 1 minus x squared raised to 2 plus 2 times zeta 2 times x raised to 2 semicolon y3 oops 3 is equals to square root 1 plus 2 times zeta 3 x times x rather squared over square root of 1 minus x squared raised to 2 plus 2 times zeta 3 times x raised to 2, and then semicolon. Y4 is equals to square root of 1 plus 2 times zeta 4 times x raised to 2 over square root of 1 minus x squared raised to 2 plus 2 times zeta 4 times x raised to 2, semicolon. As plot is y1 0 6 0 6. Hold on. As plot y2 0 6 0 6 y3 0 6 0 6. Lastly is plot y4 0 6 0 6. Grid on, comma, title, open close parenthesis, T underscore R versus W over W underscore 0, O rather, X label, open close parenthesis, W over W underscore O, comma, Y label, open close parenthesis, T underscore R, and then press F5 to run. The blue one is for the zeta equals to 0.1. Red is for zeta equals to 0.5. Orange is for zeta that's equals to 1. And lastly, violet is for zeta that's equals to 2. Question number 4. The vibrations in the floor of an industrial plant lie in the range of 16 to 75 Hz. The combined mass of the equipment and platform is 38 kilograms, and the viscous damping ratio of the suspension is 0.2. Find the maximum value of the spring stiffness if the amplitude of the transmitted vibration is to be less than 10% of the amplitude of the floor vibration once again over the given frequency range. Solution. The differential equation of motion for the system is my double prime plus v times y prime plus k times y is equals to v times u prime plus ku. The Laplace transform equation is m times ms squared plus v times s plus k times y times s is equals to v times s plus k times u times s. To get the frequency response function, we put s is equals to j times omega. The t is equals to k plus j times v times omega over k minus m omega squared plus j v omega. The absolute value t times omega is equals to the square root of k squared plus y squared times omega squared over the square root of, open close parenthesis, k minus m omega squared raised to 2 plus y squared plus v squared rather times omega squared. Simplifying that comes to the square root of 1 plus 4 zeta squared r squared over the square root of 1 minus r squared raised to 2 plus 4 times zeta squared r squared, where r is equals to omega over omega sub n as the frequency ratio and zeta is the damping ratio. Next part. Since the absolute value of y t is equals to 0.1, the absolute value of u of t can be transposed to t, absolute value of t omega is equal, it may also be equal to 0.1. 0.1 is equals to the square root of 1 plus 4 zeta squared r squared over the square root of 1 minus r squared raised to 2 plus 4 zeta squared r squared. R raised to the fourth power is minus 17.84 r squared minus 99 is equals to 0, and the r is equals to positive negative 4.7205 and positive negative 2.1078J. The natural frequency calculated using the lowermost range of working frequency will ensure that the condition R greater than 4.72 must be satisfied for the entire working frequency range of the floor vibration, wherein R is equals to omega over omega sub n equals to f over f sub n equals to 4.72, and f sub n is equals to f over 4.72 equals to 16 over 4.72, and lastly equal to 3.39 Hz. To obtain the stiffness of the spring, we calculate f sub n equals to 1 over 2 pi times k over m, and 3.39 equals to 1 over 2 pi times k over 38. Therefore, k is equal to 1.24 kilonewton per meter.
Here in the fifth problem, it is asking for different simulations to prove the theoretical results. We use different values for k and also different input frequencies. We are also tasked to plot the input u of t and the response y of t on the same set of coordinate axes. We start off with indicating our variables. 0.2 as the damping ratio of suspension, 38 kilograms is the combined mass of the equipment and platform, and we start with 1 as the value of k. We have the initial condition given as y of 0 is equals to 4 and y prime of 0 is equals to 0. Hence, we can start by indicating our symbolic function, which is y of t. We use the function diff to solve for differential equation, and we use the double equal sign to express the differentiation. It is also important not to forget to input the following conditions. Then we use the ysolve function followed by the dsolve function to solve the equation. We use the pretty function in order to have a plain text format in our command window, as you will see later on. The function hold on is used to retain the current plot in order to add another plot inside the coordinate axis. For our second set of values, we use the symbolic function of u of x. Just like what we did on the first equation, to solve the differential equation, we use the diff function. The difference is how we use ODE2 instead of ODE is to prevent errors in the code. We repeat the process in solving a differentiation equation to get the second set of values. In order to plot the function, the command fplot is used to plot the solved differentiation equation. We input fplot ysolve and fplot usolve in order to plot them both in one coordinate axis. Hold off is then used to finish the code, and then we run the script in order to view the figure made in the command window. As you can see, in this part, you can see the vibration. The moment it hits the passive vibration isolation, it dampens the wave, thus supporting our theoretical solution. This is repeated 3 more times with different values of k. We have k equals 3, k equals 5, and k equals -1. That is all. Thank you.